Hi everyone, in this tutorial I will do a deep dive into the GoogLeNet architecture, also called Inception V1. I will first show you how to use GoogLeNet by training it with Pytorch using the Cypher 10 dataset. Then I'll walk through the original paper called Going Deeper with Convolution. Finally, I'll open up the hood of the Pytorch implementation and explain it line by line. Check out the timestamp to fast forward to a specific section. So in this section we're going to use GoogLeNet on Cypher 10 and I'm going to show you how to use it and how to train it properly because there's some particularity. At the start here, there's a pre-processing that we need to do on the image that we feed the network. So we resize, we center crop here, move it to tensor, and then there's this mean and standard deviation that we need to normalize the data in. You have to watch out though, because there's a parameter in the network which can do this motion internally for the mean and standard deviation. It's set to false by default, but you shouldn't be doing the two, otherwise you will screw up the mean and the standard deviation. Okay, so just to test here, we're going to do simple batch size of 4. Here's the class, it's Cypher 10, not 100. And then we're going to load the data here and we're going to use our pre-processing here for the transform. The model is loaded from Torch Vision. So it's model GoogLeNet. This is the one that we're going to review in a few. We're going to set it to 10 classes because it's Cypher 10. If you look at the model as printed here, you're going to see it's fairly verbose and there's a lot of layers, especially for like a 22-layer network. It's fairly big. The reason for that is that the Inception's modules have 4 branch each. So you get for one layer, you get 4 branch, and then for the other layer, you get 4 other branch. And there's other branch that are auxiliary. So it's making this a bit too big. We're going to review that at the end of the video. So how we're training this thing, we use cross entropy loss over here, stochastic gradient descent with momentum. I'm using my TPU over here from Google, thank you very much. So I need to take my model and put it on the device, same thing for my data over here. There's one thing that is very important for GoogLeNet is that part. You have to take out the loss from the 3 branches during the training, because that's how originally was trained. There were 3 branches in the network, and then the resulting loss were kind of averaged together using weight. You need to do that in the training, but not at testing. So this has to be different. At testing, the loss of the main is important. So we take the 3 losses over here. So it's the output of the model.logits, aux.logits1, aux.logits2. And then the author said that they were using a 0.3 discounted weight on the auxiliary branch, and we picked 0.4 for the loss to have 100 over here, and then we take the backward step and the optimizing step. If we look at the performance, we see we started pretty high, and then we're just going down. We're just doing 2 epoch here, but already it's not too bad. Like at the end, we're getting some pretty good result here. If we look at what the average on the testing look like, it's about 70%, which is good because we have 10 classes, so it's not random. So we're training this thing properly. Maybe with more epoch, we could get a better result. And you see here for the testing, I'm only using the output of the main branch, not the other branch. So that's that. And if you look at where this network has the most trouble, it seems to be like organic things. So bird, cat, deer, dog, frog, all of these it has pretty much some difficulty. The rest, it's pretty good. So overall, I think good performance here. Don't forget for that part, this one is important. In 1998, LeNet, the 5-layer convolutional network from Jan LeCun, kicked off a revolution in the computer vision field. In 2012, AlexNet built upon the LeNet idea by adding more convolution layers and by adding a greater number of feature filter per layers. The performance of these networks seemed to hint that better neural network had to be wider and deeper. However, making network wider and deeper is more computationally expensive. This is an issue when you want to embed neural network capabilities inside mobile and embedded computers, which was something that Google was very interested in doing at the time. The authors of Going Deeper with Convolutions wanted to make these practical use cases a reality, so they set forth to build an architecture that was both performant and computationally optimized. The resulting network called GoogLeNet, or Inception, is a fairly deep and wide network with multiple submodules. Let's take a look at the high-level components. At the start of the network, we have the typical convolution and pooling structure. The others made use of local response normalization at the start, which is a cool technique inspired by the retina. It's kind of useless now because of the more modern regularization method like batch norm and dropout that work much better. The type of pooling used in this network is max pooling, which is in a nutshell takes the largest element in the subsquare of a filter to reduce the height and the width of a layer. This helps with giving the network shift and variance and prevent overfitting. Another thing you might notice at this point is the presence of one-on-one convolutions. These type of convolution layers were popularized by the Network in Network Architecture, which was published in 2013. These convolution layers will appear throughout the architecture. We'll see them in a second, they are very important. After the first convolution sequence, we'll see these bulky blocks called Inception Modules. These blocks have a usual brancher structure and are repeated over and over and over again. At 2 points in this 22-layer network, we'll see additional branch popping up. These branches are parallel to the main core of the network and aren't being integrated back. There are two main reasons for this particular structure. The first one is to fight off the vanishing gradient problem, which happens during training time when the network is too deep. The second reason is a bit less obvious, but equally valid in retrospect. It has to do with a term that will be used more in subsequent paper, which is implicit ensembling. Roughly, it means training a network with subpaths of different lengths to improve the performance of the overall network. This will be seen in later years with architecture like FractalNet and their drop path regularization procedure, DenseNet and their heavily connected structure that favor using different input features throughout the layers, or stochastic depth, which stochastically train a network for different depth per mini batch. Having multiple subpath networks that are combined to make an inference strengthen the performance of the whole network generally. Finally, at the end of the network, the inference head make a final classification. During tested time, this final branch is the only one that we use, the other one will be shut off. If we look at the full network pattern, we will have this grid, which we'll go through thoroughly in an instant. There is one new nomenclature that isn't obvious from the get-go, which is the Inception Module. Let's dive into them. The other main idea for making deep neural network more performant was to have a sparser architecture to mimic the visual system and repeat that component that they found that was optimal across many layers. That component is what they call an Inception Module, which is made of convolution layers of various resolution. We have a 1x1, 3x3, 5x5, as well as a max pooling layer. In the early layers, the 1x1 convolution really had feature filters that are highly relevant to discriminate local components. In later layers, the 5x5 convolution will be useful to create more global features from the inputs. However, this structure is very costly as the 5x5 convolution gets very expensive as the number of filters increase, especially given that pooling only reduces the height and the width of the input, not the number of filters. So, this structure, although an optimal choice to have a sparse architecture, is prohibitive computing-wise. This wasn't acceptable for the purpose of the researcher, so optimization was sought for. This is where the 1x1 convolution that we've discussed briefly in the beginning comes in handy. A 1x1 convolution is very useful to reduce the dimensionality, like a pooling layer, but in the number of filters domain. This type of filter dimensionality reduction will be reused in later years in the residual neural network architecture with what we call the bottleneck block on the right. These blocks reduce the computation by reducing the number of filters before a more expensive 3x3 filter computation. And as a side note, a 1x1 convolution is also able to increase the number of filters. So increase and decrease, both of them. In this particular case, as we see on the screen, it reduced the filter size from 256 to 64 before making a jump back to 256 to do the addition operation. Back to GoogLeNet. Taking this one-on-one convolution idea, we get the following structure now. The 1x1 convolution on the left is left untouched. We had a 1x1 convolution before the expensive 3x3 to resize number of filters. Same for the 5x5, and we add a 1x1 convolution after the 3x3 max pooling to modulate the number of filters. This makes the Inception module have a sparse architecture as well as being performant, which was the original idea of the paper. Let's work through each of the components. We have the initial 7x7 convolution followed by a 3x3 convolution. In between these two, there is a 1x1 convolution which appears in the columns 3x3 reduce. It's a bit confusing, but it's there. Whenever you see the element in the reduce column, it means there's a 1x1 convolution involved. We have all of our max pooling layers scattered across the network to cut the width and the height of the inputs. Then we have the various Inception module we've seen previously that are repeated a few times. Note that we have dropout applied at 40% at the end before the prediction. As a reminder, dropout will randomly shut off neurons where it's applied to prevent co-adaptation of activation. There's also a dropout of 70% applied in the auxiliary branch. In the patch size stride columns, we have our various definition of kernel and stride. Then we have the output size from a given layers. We have the depth of a layer, meaning how many layers within that layer there is. Then it's the number of output filter for the first branch. This is the output filter for the one-on-one convolution that does dimension reduction before the 3x3. Same for this column, but for the 5x5. This represents the output number of filter for the 2x3 convolution. This is for the 5x5 convolution. Finally, this is the 1x1 convolution after the pooling. To get the output number of filter for a layer for the concatenation operation, you need to do 1x1 plus 3x3 plus 5x5 plus pooling proj. Finally, the column param is the number of parameters that that given layer is adding to the network. Also, in terms of structure for the auxiliary branch, we have the following: average pooling at the start, 1x1 convolution to reduce dimensionality, fully connected with dropout, and another fully connected for prediction. The main dataset that I used here for GoogLeNet was ImageNet, which is a 1000 class dataset used for image recognition problem. The training procedure for GoogLeNet was straightforward. It was stochastic gradient descent with momentum, dropout at 40% for the main branch, 70% for the other branch, and they experimented with various image sampling methodology to boost performance even more. The main network they were comparing against was MSRA with the spatial pyramid pooling technique, and VGG, which had a similar overall performance. For the classification performance, GoogLeNet was the most performant entry in 2014. The results were obtained with an ensemble of 7 GoogLeNet models. Explicitly ensembling various neural network models has a great impact on the overall system performance. For the object detection performance, GoogLeNet was once again the most performant model. The ensemble of 6 GoogLeNet had around 3% better mean average precision than the second class net. However, it's important to note that Deep Insight, the model here, had better performance with a single network by about 2%. Okay, now that we have a good understanding of the philosophy behind GoogLeNet and how it performed, let's jump into the Pytorch implementation. So here we are in the code base. What I did was I took the Pytorch code straight from the documentation. I just copy pasted here, and I have a README that explains each of the bits. So this is on my GitHub. I will put a link to the description. If we look at the overall architecture here, we have our GoogLeNet class that will have the main of the architecture. Then we have the Inception module, the Inception auxiliary module. So this is like the branch that goes out, the 2 branches. There's this basic conv 2D thing. We're going to look at it in a few, but basically it's like the convolution layer. They have batch norm in this implementation because it was just better to have it this way. This is not like the actual implementation of the paper because in the paper there should not be any batch norm applied. It didn't exist at the time. And this is the GoogLeNet main API that we can call. Okay, so if you follow the README, we're going to go from the API to the internal. So GoogLeNet over here, this is the function that we can call. There's all of these parameters that we can give to pre-train the model. We're not going to pre-train it here. What is interesting for us is like the actual structure of the model. So the important point is this part. It's the model GoogLeNet here, and then with the quarks. So we just feed the all the variable that we have over there. The rest is just to instantiate the weight if we want to have it pre-trained. So before I jump into GoogLeNet, what I would like to do is look at all of the different blocks because GoogLeNet will just compose them. So let's take a look at the Inception block. So Inception looks like this. There's the parameters over here. This is the constructor, and this is the private forward and then the forward function. And remember the Inception module, not this one, is this one, right? We're gonna compose this to make it work. If we look, the parameters are these ones. It's not named in the implementation, but if you look at Inception, the constructor, you have the in channel, the channel 1-on-1, channel 3x3, 3x3 here again. This was with the reduce. This is the reduce. This is the 5x5, and then the pooling projection. These nomenclature map to these column. So we have to get the two together in order to understand what the heck is going on. But it's fairly straightforward. And you see, like the input of one is going to be the output of the second one. So if we look here, when we're going to create the stuff, The first branch is just a 1 by 1 with the kernel size of 1 here. So you have input channel and then 1 by 1 channel. And then the second branch is when you have the 3 by 3. So you have input channel and then 3 by 3 reduce. This is the output of the 1 by 1. This is the 1 by 1 kernel. And then you have the 3 by 3 reduce, which is the output of that. You're just going to feed it here. And then you have the 3 by 3. We're going to call this sequential here. And then we're just going to make 2 conv block over there. This is a 3 by 3. Watch out. In the Pytorch implementation, there's a known bug. So you have two 3 by 3 instead of 1 3 by 3 and 1 5 by 5. The reason for that is they copied this from TensorFlow, and in TensorFlow there was a bug on the implementation. There's a closed issue on this in order to change it because they didn't want to retrain the whole model. And anyway, this is a historical model, so there's not many use case. But I find it a bit, to be honest, I find it a bit wasteful to have 2 branches that are doing kind of the same exact thing. So either we take it and do 5 by 5, or we just delete this branch completely and we retrain anyway. But this is a side detail. So the performance you've seen at the beginning is with these 2 branches together. Lastly, we have the 4th branch here, which is the 1 by 1 followed by the max pooling followed by the 1 by 1. If we look at the forward functions, we have the first forward, which is the one that will be called at all time, which we'll call the private forward. And what we do in the private forward is we just take the input and then we pass it through all the branches and we return an array. And this array, we're just going to concatenate it so that we take all of the feature filters and concatenate it in the right direction. This will be moved forward into the network. So if you looked at the constructor, you've seen this conv block thing, right? It's actually set up here as basic conv2d. You could theoretically give it a conv block that is similar to what was in the paper by not putting this to none, but by default you have this basic conv2d. So let's dive into it. The basic conv2d is simple. It's basically the usual conv batch norm ReLU motion. So if you look here, we're instantiating conv here with the input and output channel and with all of the parameters that we need. And then you have the batch norm thing here, which is batch norm 2D, the output channel here. And then when you do the forward, you're going to do conv batch normalization ReLU. That's all there is. In the paper, it was not that. There was no batch norm. Let's take a look at Inception auxiliary now. Fairly straightforward, but with these 3 blocks, we can create the whole GoogLeNet. So InceptionAux, what you have is you have the constructor over there, and then you have the forward. It's fairly straightforward. So if you look, we're doing the same trick here to create the conv block, and then you have input channel for the first conv block with the 128 here, and then the kernel size would be 1 by 1. Then you have the fully connected layer 1, the second one, which will output number of class that you've defined. And then we instantiate or drop out also. In the forward function, we're going to do average pooling, right? Convolution, and then we're going to do our fully functional layer with the ReLU afterward, then the dropout in between here. So this is where the dropout will happen. And then we're going to do the fully functional, fully connected layer afterward. So it's this figure. So average pooling, conv 1-on-1, fully connected, and then the output. Yeah, and then usually the dropout layer here is 70%. It's well defined at the top of GoogLeNet. Let's take a look at GoogLeNet now. So number of class by default is ImageNet. It's 1,000. You have to bring it down to 10. If you're using Cypher, or you have to bring it to the number of class you need. Aux_logget here is set to true by default because it will move the stuff in the auxiliary branch. See here, dropout is set to 0.2 for the main branch and 0.7. It should be 0.3 here, I believe, from the paper. Anyway, that's a default variable that we have. And then the blocks that we have is basic conv2d, inception, and then inception auxiliary. You have the initialization stuff that we're doing. You're going to see this one is very verbose, and it's fine like this. It's better to have it verbose like that than to have weird for loop in between. We instantiate our auxiliary branch over there. Average pooling, we're initialize the weight. There's this thing that I've talked in the beginning of the video. If you set the variable, which one is it? Transform input to true, We'll transform the input, and these variable, this one, is a mean and standard deviation that we should change for the input. It's better to do it on the whole dataset before, and then you don't have this transformation happening during inside the network. Then you have the private forward pass, and then you have the actual forward pass here. Let's take a look at each part one by one. So the forward pass, here we're taking the input and then we're transforming it if we need to, but we're like, it's false by default. Then we're gonna go through the forward, and then we're gonna get the tree output. These three output is what we're gonna return, and we're gonna return in this weird format, GoogLeNet outputs. It's a name tuple. You have the X, the aux2, and aux1. And in this particular case, you will need to do the manipulation that I've done into the training in order to make it work. But the rest is not that important. So let's actually take a look at the init function, and then we're going to look at the private forward function. So init here, like I said, there's the three blocks that are important. The layer initialization is very, very verbose, and it's match exactly that part. So you take these this table, and then if you follow it, you will see like this is the first convolution block. You have a kernel size of 7 right here, 7 by 7. It's this one. Stride of 2, yes, it's over there, and then you're gonna get this input, the output size of that much. So you're gonna see the 64 here, and then it's with 3 channel. That's that, and you can continue like each of the different row in this thing. So the weighted initialization just below of the constructor is how we're going to initialize every layers. So we iterate in all of the modules, and then if it's an instance of count 2D, we're going to do this. If it's batch norm, we're going to do that. The standard stuff. The GoogLeNet forward is where like the input will be just fed. So you take the input, and then you're going to go here. This one is really well written because it will show you exactly what's happening step by step. There's no for loop here. It's very straightforward. So it's there. This, you can look at this, and it will just follow exactly the same spot. There's two parts that are important here and here. These correspond to the different branches. So if we're training, we're going to do this. If we're not training, we're not going to do this, and we're just going to jump over it. So this will save a bit of computation. But this will be the output auxiliary 1, auxiliary 2, and we're going to return these three things. And that's it. Pretty straightforward. All right, everyone. I hope this was useful. Don't hesitate to leave a comment if you have a question or a request for another deep neural architecture review, and see you all next week.